Some comets tumble, others flare. But 3 Atlas did something no comet should ever do. It hit the brakes on its way to the sun, then changed its mind and started accelerating. Before you dismiss this as impossible, before you click away thinking it's tabloid speculation, hear this: we have new images that confirm the phenomenon. Images from some of humanity's most sophisticated telescopes. Images that show an interstellar visitor executing what looks for all the world like a controlled maneuver. On your screen right now, if you were watching, would sit 2 photographs side by side. The first, captured by the Hubble Space Telescope on July 21, 2025, shows a comet glowing with unusual brightness, its tail pointing directly toward the sun. Not away from it, as every physics textbook says it should. Toward it. Like it's fighting gravity itself, pushing against the solar wind. The second image, taken weeks later by the Nordic Optical Telescope, shows the same object. But now its tail streams away from the sun exactly as nature intended. Between these 2 moments, something changed. Something that shouldn't be possible according to our understanding of how comets work. This is 3I Atlas, the third confirmed interstellar object ever detected. A visitor from beyond our solar system carrying with it the chemistry and secrets of another star's planetary system. And it's doing things that make astronomers uncomfortable. Here's what keeps them awake at night. When a comet vents gas and dust into space, it creates thrust, like a rocket engine firing. That thrust should show up in the orbit, creating small but measurable deviations from the path that gravity alone would predict. But 3I Atlas shows no such deviation. Its trajectory matches what pure celestial mechanics demands within the margins of measurement error. So we have an object that appears to reverse its emission pattern entirely, creating thrust first in one direction and then the opposite, but leaves no trace of that thrust in its motion through space. It's like watching a car accelerate without seeing it move forward. The timing is suspicious too. This reversal occurred gradually between July and September as the comet descended toward the inner solar system, as if something inside knew that perihelion was approaching, as if the object was preparing for its closest encounter with our star. Perihelion arrives on October 29, 2025. That's the moment of maximum heating, maximum stress, maximum activity. What happens to 3I Atlas during that passage will either confirm it's an exotic but natural comet or deepen the mystery into something that demands answers we're not ready to give. Tonight, we explore what this ancient wanderer might be trying to tell us about itself, about the galaxy it traveled through, and perhaps about the possibility that we're not alone in sending our technology between the stars. We'll examine 3 explanations. The first, grounded in ice physics and compositional transitions, represents the conservative interpretation that most scientists favor. The second explores unusual but still natural phenomena, edge cases that push our understanding. And the third is where things get interesting, where careful scientists start using phrases like engineered object hypothesis and controlled propulsion. The stakes couldn't be higher. If 3I Atlas is natural, it expands our understanding of interstellar comets, teaching us about planetary system formation around other stars. If it's something else, we're facing a discovery that would rank among the most consequential in human history. We have weeks, not years, to find out. The object is approaching its closest point to the sun. After perihelion, it will race back toward interstellar space, fading from view as it recedes. This is our window, our chance to look carefully at something that traveled light years to pass through our neighborhood. Let's begin. The story begins in the Atacama Desert of Chile, where the sky is so clear that stars don't twinkle, they burn with steady ancient light. This is one of the driest places on Earth, where rain is measured in decades rather than seasons. The air is thin, transparent, perfect for watching the cosmos. Here on the night of July 1, 2025, a telescope made a discovery that would ripple through the astronomical community like a stone thrown into still water. The telescope is called ATLAS, the Asteroid Terrestrial Impact Last Alert System.
It's not one instrument, but a network with eyes stationed at multiple sites around the world. The Chilean facility at Rio Hurtado operates autonomously, scanning the sky night after night, looking for things that move, asteroids that might threaten Earth, comets awakening as they approach the sun, anything that wasn't there yesterday but is there tonight. On that July night, Atlas found something. A faint smudge of light in the constellation Virgo moving against the background stars. The automated system flagged it, measured its position, and filed a report. Within hours, other telescopes were swinging around to confirm the detection. Initial observations revealed something extraordinary. The object's velocity was wrong. Too fast, way too fast to be gravitationally bound to our sun. When astronomers calculated its orbit, the solution came back hyperbolic. Not elliptical like the billions of asteroids and comets that belong to our solar system. Hyperbolic meaning it came from somewhere else. This was only the third time in human history that we'd confirmed such an object. The first was Oumuamua in 2017, that mysterious cigar-shaped visitor that passed through too quickly for detailed study. The second was 2I Borisov in 2019, which looked more like a typical comet and gave astronomers hope that interstellar visitors might be understandable after all. Now 3I Atlas. The designation tells its story, 3I for the third interstellar object, Atlas for the survey that found it. A name that sounds more like a password than something that traveled between stars. But unlike Oumuamua, which showed no signs of outgassing despite its unusual acceleration, 3I Atlas was clearly active. Even in those first observations, it displayed a faint coma, the fuzzy cloud of gas and dust that surrounds an active comet's nucleus. This was good. Comets, we understand. Comets follow rules written in ice and sunlight. The Hubble Space Telescope, humanity's premier optical observatory, turned its gaze on the new visitor on July 21st. The image it captured would become the first piece of our puzzle. A bright, compact nucleus surrounded by a glowing coma, but there was something odd about the morphology, the shape and structure of the emission. A forward-pointing brightness that shouldn't have been there. Simultaneously, the James Webb Space Telescope, our most powerful infrared eye, observed 3I Atlas with its near-infrared spectrograph. The spectrum revealed something stunning, unusually high levels of carbon dioxide in the comet's coma. Not just high, among the highest CO2 to water ratios ever recorded for any comet. This was a clue. Carbon dioxide sublimates transitions from ice to gas at much lower temperatures than water ice. A comet rich in CO2 could start outgassing far from the sun, out where temperatures are still frigid. The composition suggested this object formed in a very cold environment, colder even than the outer reaches of our solar system. By early August, orbital solutions were solid. 3I Atlas was approaching from the direction of the constellation Hercules, coming in at a steep angle to the plane of the solar system. Its velocity relative to the sun was approximately 33 kilometers per second, faster than anything gravitationally bound to our star could achieve. Working backward, astronomers estimated the object had been traveling through interstellar space for potentially millions of years, maybe longer. Time enough to cross light years of emptiness. Time enough to pass through clouds of interstellar gas and dust. Time enough to be bombarded by cosmic rays that slowly alter surface chemistry. The size was harder to determine. You can't measure the nucleus directly when it's wrapped in a coma of gas and dust. Instead, astronomers used the object's brightness, made assumptions about how reflective its surface might be, and worked out estimates. The calculations suggested a body several kilometers across. Not enormous, but substantial, comparable to some of the larger comets that occasionally grace our skies. As August progressed, more telescopes joined the observation campaign. The Nordic Optical Telescope in the Canary Islands, the Gemini Observatory in both hemispheres, the Keck telescopes atop Mauna Kea in Hawaii. Each facility contributed data, building a composite picture of this interstellar wanderer, and that's when the strangeness began to emerge. Not all at once, not in a single shocking observation, but gradually. Like watching a photograph develop in a chemical bath, details appearing where before there was only blank paper. The tail was changing, not just growing, which would be normal, as the comet approached the sun and heating intensified. Changing direction, reorienting, doing something that comets aren't supposed to do. This is where our mystery truly begins. In the documented transformation of 3I Atlas between July and September 2025, in images that show the impossible happening in slow motion, frame by frame, night by night. The baseline was established. We knew what we were looking at. An interstellar comet, the third ever confirmed, approaching the inner solar system on a hyperbolic trajectory. Active outgassing displaying a coma rich in carbon dioxide. Now we needed to understand what it was doing, and why. Let me explain something about comets that you probably learned in school but might have forgotten. When a comet approaches the sun's solar radiation and the solar wind push on the gas and dust streaming off the nucleus. This creates the tail, that beautiful streamer that always points away from the sun. Always. It's one of the most fundamental, reliable features of cometary behavior. A comet's tail is basically a cosmic windsock showing you which way the solar wind is blowing. And the solar wind always blows outward from the sun, carrying with it the charged particles of the solar atmosphere at speeds of hundreds of kilometers per second. So when the Hubble Space Telescope captured that July 21st image showing 3I Atlas with a tail pointing toward the sun, astronomers took notice. This is what's called an anti-tail. And before you think this is unprecedented, let me be clear, anti-tails have been observed before. They're rare, but they happen. The most famous example was Comet Arend-Roland in 1957, which displayed a spectacular sun-facing spike that made newspapers around the world. But here's the thing about classical anti-tails. They're usually projection effects, optical illusions created when Earth passes through the plane of a comet's orbit. Large dust particles too heavy to be pushed strongly by radiation pressure lag behind the comet along its orbital path. When viewed edge-on, this trail of trailing particles appears to point forward, creating the illusion of a sun-facing tail. The key word there is illusion. The particles aren't actually moving toward the sun. We're just seeing their spatial distribution from an angle that makes it look that way. So when 3I Atlas showed its anti-tail, the first assumption was projection effect. Viewing geometry. Nothing to see here, just physics being weird the way physics sometimes is when you view three-dimensional structures from different angles. But then the Nordic Optical Telescope began its monitoring campaign. Through July, August, and into September, the KNOT captured image after image, documenting the comet's evolution as it descended toward perihelion. And what those images showed was difficult to explain with viewing geometry alone. The sun-facing emission was fading, gradually, systematically over weeks. Meanwhile, a classical anti-solar tail was growing, strengthening, extending outward like a comet tail should. The transition was smooth, continuous, as if the comet was exhaling in one direction and then slowly, deliberately switching to exhale in the opposite direction. Frame by frame, you could watch it happen. The forward glow dimming, the rearward tail brightening. Not a sudden flip, not an instantaneous reversal, but a gradual reorientation that played out over the better part of 2 months. Astronomers ran the geometric models. They calculated how Earth's position relative to the comet changed during this period. Yes, our viewing angle shifted. Both Earth and the comet were moving, altering the perspective. But when you correct for those changes, when you account for how projection effects should manifest, the reversal remains. This wasn't just us moving around the comet and seeing different sides of a static dust distribution. Something about the emission pattern itself was changing. The composition of the material being shed appeared different too. Early spectra taken when the anti-tail was prominent showed strong carbon dioxide emission. Later spectra after the reversal showed more water vapor and refractory dust, rocky particles mixed with ice. The morphology evolved in ways that suggested the character of the outgassing had fundamentally changed. The compact, forward-scattered glow of July gave way to the extended, more diffuse tail of September.
Different emission, different scattering properties, different dynamics. Here's where we need to talk about what jets do to a comet's orbit. When material streams off a nucleus, it carries momentum. Conservation of momentum means the nucleus must recoil. It's exactly like a rocket throw mass out the back, and you accelerate forward. For comets, these non-gravitational forces are well documented. They show up as small deviations from the purely gravitational orbit. The comet ends up slightly ahead or behind where pure Newtonian mechanics says it should be, sometimes above or below the orbital plane. These non-gravitational accelerations are tiny but measurable. They're caused by asymmetric outgassing jets that preferentially point in certain directions, creating net thrust. Now, if 3I Atlas was venting material toward the Sun in July, that should create a braking force. Thrust pointing sunward means acceleration opposing the comet's orbital motion, slowing it down relative to the pure gravitational trajectory. Then, if the emission flipped and material started streaming anti-sunward in September, that should create acceleration in the opposite direction. Forward thrust, speeding the comet up along its orbit. These effects should be visible in the astrometry, the precise measurements of the comet's position over time. The orbit should deviate. The object should be somewhere different than where gravity alone would put it. But here's the puzzle that keeps astronomers up at night. 3I Atlas doesn't show significant non-gravitational acceleration. Its trajectory matches what you'd predict from the Sun's gravity and the gravitational perturbations of the planets. The orbital residuals, those tiny differences between predicted and observed positions, remain within measurement error. It's as if the jet reversal is happening without mechanical consequence. As if the comet is somehow balancing its books, creating thrust that produces no net acceleration. There are three ways to explain this. First, the object is so massive that the recoil from outgassing is negligible. A supertanker doesn't lurch when someone tosses a rope off the deck. Maybe 3I Atlas is the supertanker of comets. Second, the outgassing might be more symmetric than it appears. Maybe there are multiple jets firing in different directions, and we're only seeing the brightest ones. The net force could average to nearly zero if thrust vectors largely cancel out. Third, and this is where we start to edge into uncomfortable territory, maybe something else is going on. Something that doesn't follow the standard sublimation-driven model that explains every other comet we've studied. But we're not there yet. Not yet. First, we need to understand what the conservative interpretation says, what ice physics alone can explain, because the truth is, ice is strange. Ice is complex. Ice can surprise you. And when you're dealing with ice that formed around another star in conditions, we can only guess that surprises should be expected. The anti-tail reversed. That much is documented fact confirmed by multiple independent observatories with different instruments. What caused that reversal, what it means for the object's nature, that's where we're headed next. But let me leave you with this thought. Every comet that approaches the Sun is conducting an experiment. Heat hits ice. Physics happens. Usually, we understand the results. With 3I Atlas, we're still trying to read the data.
Let's talk about numbers. Because in astronomy, numbers are where speculation meets reality, where hunches either survive or die. Between July and October 2025, 3I Atlas shed approximately 2 million metric tons of material into space. Let that sink in for a moment. 2 million tons. That's roughly the mass of 3 Empire State Buildings evaporating into the void over the course of a few months. How do we know this? Through careful measurement of brightness and composition. When dust and gas scatter sunlight, they reveal themselves through the glow they produce. Telescopes measure that brightness at different wavelengths, applying conversion factors that account for particle size reflectivity and geometric distribution. The process is called photometry, and it's more art than science. You have to make assumptions about what the dust looks like, how much light it reflects, how it's distributed in space. Change those assumptions, and the mass estimate changes. But even accounting for uncertainties, the number comes out in the range of millions of tons lost over the observation period. That's a lot of material. And here's the uncomfortable part. When you eject that much mass, you create thrust. You have to. Newton's third law applies as reliably in deep space as it does here on Earth. Let me walk you through the calculation because this is where the mystery gets mathematical. When gas sublimates off a comet, it expands rapidly. Carbon dioxide heated by sunlight rushes away at speeds of several hundred meters per second. Water vapor moves slightly slower. Dust grains dragged along by the gas flow accelerate to speeds depending on their size. Take the mass loss rate 2 million tons over roughly 100 days, and you get about 230 kilograms per second on average. That's the mass flow rate. Multiply by the velocity of the ejected material, let's say 400 meters per second, as a reasonable estimate for a mix of gas and dust, and you get the thrust force. Force equals mass flow rate times exhaust velocity. It's the fundamental rocket equation. The calculation gives you a force of about 92,000 newtons. That might not sound like much, but remember, this force is acting continuously day after day on an object floating in space with no friction to slow it down. Now calculate the acceleration that force would produce. Force divided by mass equals acceleration. And here's where we need to know the mass of the nucleus for the observed lack of orbital perturbation. To make sense, the nucleus must be massive enough that 92,000 newtons of thrust barely budges it. Working through the math, accounting for the fact that thrust acts over months, not seconds, you get a minimum mass estimate. That minimum comes out to approximately 33 billion metric tons. 33 billion tons. To put that in perspective, that's about half the mass of Comet Halley, the most famous periodic comet in history. It's in the range of some of the larger comet nuclei we've studied up close with spacecraft. If you assume a density similar to typical comets, around 600 kilograms per cubic meter, that porous mixture of ice and dust and rock, you can back out a size. The calculation suggests a body several kilometers across, maybe 2 to 3 kilometers in diameter, possibly larger depending on shape and density. The uncertainty range is substantial. If the dust particles are moving faster than we estimated, the mass calculation comes down. If outgassing is more anisotropic, concentrated in narrow jets rather than distributed evenly, the recoil might be directionally biased in ways that partially cancel, making our mass constraint weaker. If a larger fraction of the lost mass is fine dust rather than gas, the momentum transfer changes because dust accelerates more slowly and might not contribute as much thrust per unit mass. Imagine running a Monte Carlo simulation, exploring different combinations of parameters within their plausible ranges. Each run generates a mass estimate. The distribution of results shows a peak around 33 billion tons, but it spreads across a factor of 3 in either direction. This is the honest uncertainty of astronomical inference. We're translating observed light into physical properties across hundreds of millions of kilometers of space. Precision is elusive. But even with all that uncertainty, we're left with a puzzle. An object losing millions of tons of material, creating thrust that should perturb its orbit but showing no detectable perturbation. An object massive enough to shrug off that thrust as inconsequential. 3 scenarios could explain this situation.
Scenario 1. The object is genuinely massive enough that outgassing thrust is negligible. This is the straightforward interpretation. Big comet proportional outgassing physics as usual. No mysteries required. Scenario 2. The outgassing is unusually symmetric. Jets firing in multiple directions such that thrust vectors partially cancel.
Some comets do this. Active regions on different parts of the surface produce emissions that, when summed, average to nearly zero net force. Scenario 3. Something non-cometary is happening, some mechanism that doesn't follow the standard model. That third option is where speculation lives. If 3I Atlas were maneuvering using some controlled propulsion system, you'd want the thrust to be balanced or variable in ways that don't produce random orbital changes. An engineered object maintaining a specific trajectory would minimize detectable non-gravitational forces outside its intended maneuvers. The math doesn't prove this interpretation, but it doesn't rule it out either. And that's enough to keep the question alive in the minds of some researchers. The size estimate matters for another reason. Interstellar space is hostile. Cosmic rays bombard any object traveling through the galaxy. Over millions or billions of years, those high-energy particles erode surface material, alter chemical composition, create radiation damage layers tens of meters deep. Smaller objects suffer more because they have higher surface area to volume ratios. A body several kilometers across has enough mass to survive its interstellar journey relatively intact, maintaining a substantial volatile inventory that can activate when it passes through a star system's warmth. Compare this to Oumuamua, that first interstellar visitor, which was probably only a few hundred meters in size based on brightness and assumed composition. Oumuamua showed significant non-gravitational acceleration despite no detected outgassing, a puzzle that generated years of debate and multiple competing explanations. 3I Atlas, being much larger, should produce observable outgassing if it contains volatiles. And it does, but the absence of corresponding orbital changes given that large mass loss creates its own puzzle. What happens next depends on perihelion. The close solar passage will heat the nucleus to maximum temperature, potentially triggering fresh outgassing from previously dormant areas. If the mass loss rate increases dramatically, as often happens when comets round the Sun, we'll get better constraints on nucleus properties from the enhanced activity. If the orbital residuals suddenly jump, showing clear, non-gravitational acceleration during or after perihelion, that tells us something changed about the outgassing pattern. Something activated or deactivated in ways we can measure through motion as well as brightness. The data collected in the next few weeks will either tighten these mass constraints or reveal new anomalies that demand explanation. But for now, we're left with an uncomfortable truth. The numbers work if the comet is big. The numbers work if the thrust cancels out. The numbers work if something else is going on. All three explanations remain on the table. And that's rare in astronomy. Usually by this point, with this much data, one explanation clearly dominates. Not this time, not yet.
Now we come to the conservative explanation, the one that requires no new physics, no exotic assumptions. Just the complex but understood behavior of ice and dust under solar radiation. This is the explanation that most comet scientists favor, and honestly, it should be your default too. In science, when faced with something unusual, you first exhaust all mundane explanations before invoking the extraordinary. It's called Occam's razor, and it's saved scientists from embarrassment more times than anyone can count. Abraham Loeb and Adam Kito, two astronomers who've spent considerable time thinking about 3I Atlas, published a model that attributes the jet reversal to compositional changes in the sublimating volatiles. Their argument flows from first principles about how different ices behave at different temperatures and distances from the Sun. Let me walk you through their logic because it's elegant, and possibly correct. Start with carbon dioxide ice. CO2 sublimates transitions directly from solid to gas at temperatures far below the freezing point of water. Even at the chilly distances beyond 3 or 4 astronomical units from the Sun, carbon dioxide molecules can break free from their crystalline lattice and stream into space. An astronomical unit for reference is the distance from Earth to the Sun, about 150 million kilometers.
At 3 AU, solar heating is weak. Surface temperatures are far below 0 Celsius. But that's warm enough for CO2. The gas expands rapidly. As it does, it entrains dust particles, dragging them along through collisions and momentum transfer. These dust grains, once liberated from the nucleus, become subject to solar radiation pressure, the gentle but persistent push of sunlight that affects small particles more strongly than large ones. Now consider what happens as the comet moves inward, closer to the sun's warmth. The carbon dioxide sublimates more vigorously. Activity increases, the coma brightens, but eventually the surface layers rich in CO2 get depleted. You've sublimated most of the easily accessible carbon dioxide. Deeper material becomes exposed, and that deeper material has a different composition. Water ice dominates, mixed with refractory dust, the rocky and carbonaceous particles that don't sublimate at all but rather get left behind or mechanically released as the ice around them vaporizes. Water ice requires higher temperatures to sublimate efficiently. It doesn't really activate until you're well inside 3 AU in the inner solar system, where solar heating becomes intense. The dust released by water sublimation has different properties than dust entrained by carbon dioxide. The grain size distribution might differ. The release velocity is likely lower because water vapor expands less energetically than CO2. The survival distance, how far the particles travel before they break down under solar heating or get swept away by radiation pressure, changes based on composition and size. Here's where the Loeb-Kato model gets clever. They argue that this transition from CO2-dominated to water-dominated sublimation can flip the apparent direction of the emission. In the carbon dioxide phase, smaller ice-coated grains with short lifetimes scatter efficiently at optical wavelengths. These particles, released early in the comet's approach, might create a forward-scattered glow visible from Earth's viewing geometry, appearing as a sun-facing anti-tail. As the regime shifts to water and refractory dust, larger particles with different scattering properties dominate. These create a more traditional tail, pushed away from the sun by radiation pressure. The timing aligns beautifully with observations. 3I Atlas was around 3 to 4 AU from the sun when the anti-tail was most prominent. That's precisely the distance range where carbon dioxide sublimation should be active, but water ice remains mostly dormant. As the comet descended through 3 AU heading toward its October perihelion at 1.36 AU, the transition to water-dominated activity would naturally occur. The Nordic Optical Telescope images capturing the tail reversal in August and September span exactly this transitional period. Imagine a cross-section of the comet's nucleus. The outer layers exposed to space during the object's long interstellar journey are enriched in carbon dioxide ice. CO2 is more volatile than water, more likely to have been retained near the surface despite the cold of interstellar space. Deeper down, water ice dominates. It's more refractory, less prone to sublimate during the object's eons in cold storage between stars. As solar heating creates a sublimation front that advances into the nucleus, that front crosses the compositional boundary. The outgassing regime changes, and with it the observable properties of the coma and tail. This model has precedent. Astronomers have documented comets showing seasonal variations in activity, with different regions turning on and off as they rotate, and as their distance from the sun changes. Comet Hale-Bopp, that spectacular visitor from 1997, displayed multiple distinct jets from different active areas, each releasing material with slightly different composition and timing. The lesson from decades of comet studies is that these objects are heterogeneous, layered, capable of surprising behavior as thermal waves penetrate their interiors. But 3I Atlas seems more abrupt in its transition than typical solar system comets. The reversal happened over weeks rather than months or years. That rapidity suggests either a sharp compositional boundary inside the nucleus or an unusual geometry of active regions. Perhaps the initial sun-facing activity came from a specific location on the surface that became inactive as it heated past some threshold, while simultaneously a different region on the opposite hemisphere activated. Comet nuclei are irregular bodies, often with complex topography. Cliffs, basins, fractured terrain. These can focus outgassing in ways that don't reflect average surface properties. The model makes predictions that can be tested. If the compositional transition explanation is correct, spectroscopic observations should show the predicted change in gas composition. Early observations when the anti-tail was prominent should show relatively strong carbon dioxide emission lines. Later observations after the reversal should show enhanced water vapor and possibly other volatiles like carbon monoxide that sublimate at intermediate temperatures. The dust-to-gas ratio should also change with more refractory material in the later stages.
Some observational evidence supports this picture. Reports indicate spectroscopic follow-up detected compositional changes consistent with evolving volatile activity. The relative strength of different emission features shifted between July and September, matching what you'd expect if the dominant sublimating species changed. But the data remains sparse enough that alternative interpretations can't be decisively ruled out. Spectroscopy of faint, fast-moving objects is challenging. Signal-to-noise constraints mean you can't always see the subtle spectral lines that would clinch the case. The grain size distribution adds another layer of complexity. The Loeb-Keto model explicitly considers how particle size affects dynamics. Small grains sub-micron to micron scale are strongly coupled to gas flow and get accelerated to high velocities. They also have short survival times because solar heating sublimates any volatile coating quickly.
Large grains, tens to hundreds of microns across, are less coupled to gas. They move more slowly and survive longer. The balance between these populations determines what you see and where you see it in the coma and tail. The model suggests that during the carbon dioxide phase, small ice grains dominated the optical signature, creating a compact, bright emission that under certain viewing geometries appeared sun-facing. During the water dust phase, larger refractory grains dominated, creating a more extended tail that followed the classical radiation pressure-driven pattern. Weaknesses in this explanation exist, and honest scientists acknowledge them. The required compositional stratification, though plausible, hasn't been directly observed. We haven't drilled into 3I Atlas to confirm it has a CO2-rich outer layer over a water-rich interior. We're inferring structure from behavior, always a risky proposition. The anisotropy of emission. Whether jets are focused or diffuse remains uncertain. The precise grain size distribution, which is critical to the model's predictions, is poorly constrained by current observations. What observations would definitively confirm or refute this model? High-resolution imaging showing multiple active regions turning on and off would help. Time-resolved spectroscopy, capturing the moment of transition in detail, would constrain the sublimation chemistry. Polarimetric measurements revealing changes in dust properties would test the grain size predictions. And most critically, continued monitoring through and after perihelion will show whether the anti-solar tail persists, strengthens, or gives way to new behavior as the comet experiences peak heating. The compositional model represents the conservative interpretation, the one that requires no new physics, no exotic assumptions, just the complex but understood behavior of ice and dust under solar radiation. It's the explanation most scientists would favor until forced otherwise by irreconcilable observations. But as we'll see, not everyone is convinced that ice tells the whole story. The universe has a way of surprising us, of taking our careful models and revealing that reality is stranger, more subtle, more provocative than we imagined. Sometimes ice is just ice. And sometimes ice is a cover story for something else entirely.
Here's an uncomfortable truth about astronomy. We're terrible observers, not because we lack skill or instruments, but because we're stuck in one location viewing a three-dimensional universe projected onto a two-dimensional sky. Depth information collapses. Motion toward or away from us becomes invisible. What looks extraordinary might be ordinary physics viewed from an unusual angle. This is the first lesson of observational astronomy, learned and relearned across centuries. The ancient Greeks thought planets moved in bizarre loops across the sky, sometimes going forward, sometimes backward. Ptolemy constructed elaborate systems of epicycles, circles upon circles, to explain the apparent retrograde motion of Mars. It took Copernicus and Kepler to realize the motion isn't bizarre at all. We're just watching from a moving platform. In the 19th century, Giovanni Schiaparelli observed Mars and reported seeing canali channels. The word was mistranslated to canals in English, implying artificial construction. For decades, respected astronomers debated whether Mars hosted an advanced civilization that built waterways. Then better telescopes revealed the canals were optical illusions, the human eye connecting random features into patterns that weren't there. And in 1957, comet Arend-Roland displayed a spectacular anti-tail that made worldwide headlines. Many speculated about unusual physics. Then geometric analysis showed it was entirely projection dust distributed along the comet's orbit, appearing to point forward due to viewing angle. So when 3i Atlas showed its anti-tail and subsequent reversal, the first question wasn't, "What's the comet doing?" It was, "What are we seeing?" The distinction is crucial. Are we witnessing an intrinsic change in the object's behavior? Or are we watching Earth move around the object, creating an apparent change while the actual emission pattern remains constant? Let me explain how projection effects work. A comet ejects material in three-dimensional space. Gas and dust stream away from the nucleus in all directions, though often preferentially from active regions on the sunward side. This creates a complex three-dimensional structure. A coma surrounding the nucleus jets, or fans extending in various directions, and a tail shaped by solar radiation and the solar wind. But we observe this as a two-dimensional projection on the sky. Our line of sight collapses depth information, making it hard to distinguish between material moving toward us, away from us, or perpendicular to our view. As Earth orbits the Sun and the comet follows its own trajectory, the viewing geometry constantly changes. What appeared directed one way can seem to flip as our perspective shifts. The classic case is the anti-tail phenomenon known for over a century. When Earth crosses the orbital plane of a comet, dust particles that lag behind the nucleus along its orbit appear to point sunward. This happens because we're viewing the dust trail edge on. The particles aren't moving toward the sun, they're trailing the comet along its path. But from our temporary viewing angle, they project as a forward spike. Then, as Earth continues moving and crosses out of the comet's orbital plane, the anti-tail vanishes. The normal tail becomes prominent again. Nothing about the comet changed, only our perspective. Astronomers have sophisticated methods for distinguishing real changes from apparent ones. Vector tomography uses observations from multiple dates and viewing angles to reconstruct the three-dimensional distribution of material. If you watch the comet from enough different perspectives, you can invert the problem-solving for the actual spatial structure that produces the observed two-dimensional projections. This technique works best when viewing geometry changes substantially, giving you diverse angles to triangulate from. Polarimetry provides another diagnostic. Dust particles scatter sunlight, and that scattering produces polarization. The degree and direction of polarization depend on the scattering angle, the angle between incoming sunlight, the dust particle, and our line of sight. Different viewing geometries produce different polarization signatures, even if the dust distribution remains constant. Measure.
polarization over time, and you can test whether observed morphology changes are consistent with static dust illuminated from varying angles, or require actual redistribution of material. Time-sequenced imaging helps too. If you capture images frequently enough, you can watch individual features evolve, tracking their motion across the sky and relative to the nucleus. Features that are truly new, genuinely changing emission patterns will appear and evolve in ways inconsistent with simple projection of static structures. Features that are projection artifacts will shift predictably as viewing geometry changes following mathematical models of perspective transformation. So let's apply these lessons to 3I Atlas. Between July and September, Earth's position relative to the comet changed significantly. Both objects were moving Earth in its nearly circular orbit 3I Atlas on its hyperbolic trajectory plunging sunward. The geometry shifted, altering phase angles, scattering angles, and the projection of any three-dimensional structures in the coma onto the two-dimensional sky. The Nordic Optical Telescope team, who tracked the comet through this period, would have been keenly aware of projection pitfalls. Their analysis presumably included geometric modeling, testing whether the observed changes could be explained by Earth's changing position alone. The fact that they reported an intrinsic jet reversal suggests their models ruled out pure projection effects. But ruling out requires assumptions about dust distribution, ejection velocities, and other parameters. Uncertainty in those assumptions leaves room for alternative geometric explanations. One way to test this is simulation. Generate a model comet with static dust, ejection some fixed pattern of jets, or isotropic outgassing. Calculate what Earth-based observers would see at different dates as viewing geometry changes. Compare those predictions to actual observations. If the match is good, projection effects dominate. If predictions fail to reproduce observed features, intrinsic changes are required. The challenge is that real comets aren't static. Even if the jet reversal is projection, the comet is still evolving. Outgassing rates change as heliocentric distance decreases. Dust production varies. Active regions turn on or off. Rotation carries different surface areas into and out of sunlight. Separating viewing geometry effects from genuine activity changes requires careful modeling of both. Polarimetric data, if available, would help tremendously. Reports haven't detailed whether polarimetry was performed on 3I Atlas during the critical July to September period. If such data exist, they could constrain dust grain properties and scattering geometry tightening limits on projection versus intrinsic interpretations. If polarimetry wasn't done, that's a gap. Though by the time future observations could fill it, the geometry will have changed again, making direct comparisons difficult. Another consideration: the abruptness of the transition. Projection effects tend to be smooth, gradual as viewing geometry continuously evolves. A sudden flip happening over days rather than weeks suggests something intrinsic, but defining sudden versus gradual is subjective when observation cadence is irregular. If you image once a week, a change that happened over 3 days appears sudden. The same change sampled daily might look smoother. Multiple independent observers strengthen the case. If several telescopes in different locations with different instruments and viewing conditions all report the same transition, instrumental or observational artifacts become less likely. Hubble, the Nordic Optical Telescope, and potentially others form a cross-checking network. Consistency across platforms argues for reality over artifact. There's also the composition angle. Projection effects can't change spectral signatures. If the emitted material's chemistry shifted between July and September, that's intrinsic, not geometric. Spectroscopic follow-up reportedly detected compositional changes supporting the physical transition model. But again, details matter. How strong were the spectral features? What uncertainties exist? Were multiple wavelengths covered, providing robust compositional diagnostics? The risk of confirmation bias looms. Once researchers believe they've found something unusual, they might interpret ambiguous data to support that belief. Independent analysis by teams with no stake in the outcome provides a check. Have skeptics examined the data? Do alternative explanations exist that haven't been fully explored? The scientific process requires adversarial collaboration, where different groups challenge each other's interpretations, forcing stronger evidence and better arguments. By the time you account for all these factors, viewing geometry, dust dynamics, instrumental effects, observational cadence, you realize how difficult it is to claim certainty. The honest answer is that projection effects probably don't explain the full extent of the observed reversal, but they might contribute. The intrinsic jet flip interpretation is likely correct, but with acknowledged uncertainties. And those uncertainties matter when deciding how exotic an explanation to invoke. If the reversal is mostly geometry, then 3-eye atlas is interesting, but not anomalous. If the reversal is intrinsic, but explained by compositional transitions, then we have an exotic but natural comet. If the reversal is intrinsic and not fully explained by ice physics, well then we have a problem. Or an opportunity depending on your perspective. The data we have now leans toward intrinsic change, but lean isn't proof. And in science, especially when extraordinary claims lurk nearby, proof matters. We need more observations, better spectroscopy, continued monitoring through Perihelion, independent analysis from multiple teams, and we need honesty about what we don't know, because the truth is, seeing clearly is harder than it looks, and sometimes what's hardest to see is right in front of us. The universe is weirder than we give it credit for. Not alien spaceship weird, just physics we haven't fully mapped out weird. Natural phenomena can be extraordinarily strange when conditions push into extremes we rarely observe. This is hypothesis 2. 3-eye atlas is natural but occupies some unusual corner of parameter space that makes its behavior surprising without being inexplicable. Let's explore what that might look like. First, consider extreme compositional stratification. The Loeb-Kato model invokes a CO2-rich outer layer over a water-rich interior, but maybe the reality is more dramatic. Maybe the boundary between these compositional zones is knife-sharp rather than gradual. Imagine the nucleus as an onion with distinct shells. The outermost layer is almost pure carbon dioxide ice. Beneath that, a transition zone where CO2 and water mix. Deeper still water ice dominates. If thermal penetration reaches that sharp boundary abruptly, the outgassing regime could flip faster than you'd expect from smooth compositional gradients. The transition might happen over days instead of weeks, creating the appearance of deliberate reversal when it's really just extreme layering revealing itself. Why might an interstellar comet be so sharply stratified? During its formation in another star's protoplanetary disk, local conditions might have changed rapidly. Temperature fluctuations, compositional gradients in the nebula, or sudden exposure to different reservoirs of material could create layered structures. Millions of years of interstellar travel compound this. Cosmic rays don't penetrate deeply, maybe only tens of meters, so the surface layer irradiated and chemically altered during the long journey might have very different properties than the pristine interior. Second possibility, subsurface heat retention. When a comet passes through the inner solar system, the sun's heat doesn't just warm the surface. It conducts inward, creating a thermal wave that penetrates meters or tens of meters deep over weeks and months. This subsurface heating can trigger delayed outgassing. Ice deep in the nucleus sublimates and gas pressure builds until it finds fractures or porous channels to vent through. These vents might not be on the sunward side. They might emerge from the night side or from areas that seem geologically unlikely. If 3-eye atlas has an unusual thermal conductivity, maybe due to its interstellar exposure or its formation conditions, heat might penetrate deeper and faster than typical comets. This could activate water ice reservoirs while surface CO2 is still depleting, creating overlapping outgassing regimes that confuse the observational signature. Third, rotation-driven activity modulation. Most comets rotate typically with periods of hours to days. As they spin, different parts of the surface rotate into and out of sunlight. Active regions, places where ice is close to the surface and easily sublimated, turn on when illuminated and off when they enter shadow. For a comet with multiple active regions on opposite hemispheres, the brightness and jet directions can vary dramatically over a rotation period. If one region is CO2-rich and another is water-rich, you might see compositional variations that track with rotation. Now add in the fact that we don't know 3I Atlas's rotation period. If it's rotating slowly, one rotation every few days or weeks, the changes we're observing might partly reflect different active regions coming into view. The jet reversal could be region A, CO2-rich, forward-emitting, shuts down. Region B, water-rich, rear-emitting, turns on. The transition time scales with rotation period. Fourth possibility, fragmentation without visible breakup. Comets are fragile. Many consist of smaller chunks loosely held together by ice and weak gravitational attraction. When stresses from rotation, tidal forces, or thermal expansion exceed the material's strength, nuclei can split. Sometimes this fragmentation is dramatic and obvious. Comet Shoemaker-Levy 9, torn apart by Jupiter's tidal forces, broke into more than 20 fragments that later impacted the planet. But sometimes fragmentation is subtle. A nucleus cracks but doesn't fully separate. Or a small piece breaks off, remaining close enough that it's not resolved as a separate object in images but contributing outgassing that alters the overall appearance. If 3I Atlas underwent partial fragmentation during its approach, exposing fresh interior ice that could change activity patterns rapidly, new surfaces with different compositions suddenly become available for solar heating. Fifth, interstellar radiation damage creating exotic surface chemistry. During millions or billions of years traveling through interstellar space, cosmic rays bombard a comet's surface. These high-energy particles break chemical bonds, rearrange molecules, and create new compounds that don't exist in the pristine solar system. The result is an irradiated crust, maybe tens of meters thick, with altered properties. This crust might sublimate differently than normal cometary ice. It might contain molecular species we don't expect. Complex organics, amorphous carbon structures, minerals that don't form under typical solar system conditions. When solar heating vaporizes this exotic crust, the spectral signature and outgassing behavior could be unusual. Then, as the crust ablates away and pristine interior ice becomes exposed, the character of the emission changes. This is speculative. We don't have samples to confirm how interstellar irradiation affects comet surfaces. But laboratory experiments show that cosmic ray bombardment does alter ice chemistry.
Extrapolate over millions of years, and significant changes are plausible. Sixth, the possibility that multiple unusual factors combine. Nature rarely serves up single variable explanations. Maybe 3I Atlas is sharply stratified and has unusual thermal properties, and underwent partial fragmentation, and has an irradiated crust. Each factor alone might create subtle effects. Combined, they could produce behavior that looks anomalous but is still at its core natural. This hypothesis of space unusual but natural is vast. It encompasses everything from extreme but precedented physics to novel combinations of known phenomena. The key characteristic is that no fundamentally new mechanisms are required. Just rare circumstances edge cases the long tail of the distribution. How do we test whether 3I Atlas occupies this unusual but natural space? Continued observation through perihelion is critical.
If activity increases dramatically as expected for close solar passage, but the character of that activity remains within the bounds of what comets do, even weird comets, that supports the natural interpretation. If spectroscopy reveals exotic but still natural molecules, unusual ratios, unexpected ices but nothing that violates known chemistry that suggests the irradiated crust or exotic composition scenarios, if high-resolution imaging shows multiple distinct active regions, complex surface topography or evidence of partial fragmentation that explains anisotropic emission patterns without invoking propulsion. The weakness of Hypothesis 2 is its flexibility. You can explain almost anything as natural but unusual if you allow enough variables to vary. That flexibility makes the hypothesis hard to falsify, which is a warning sign in science. Good hypotheses make specific predictions that can be tested. Hypothesis 2, as broadly stated, predicts something natural but surprising is happening. That's not wrong, but it's also not terribly useful. To be rigorous, we'd need to specify which unusual natural mechanism do we think is at work. What specific observations would confirm or rule it out? The compositional stratification version predicts sharp spectroscopic transitions at specific heliocentric distances. The fragmentation version predicts possibly detecting separate components in high-resolution images. The rotation version predicts periodic brightness variations or compositional modulation. These are testable. And if tests rule them out, we narrow the possibility space. What I'm really saying is, before we jump to exotic explanations, we need to explore the full range of natural ones, because comets, especially interstellar comets, can be strange without being supernatural. The universe has had 13.8 billion years to explore parameter space. It's found corners we haven't mapped yet, conditions we haven't simulated, physics we technically understand but haven't seen played out in this particular combination. 3i Atlas might be our introduction to one of those corners. Unusual, yes. Challenging our models, absolutely. But still fundamentally natural, still ice and rock and dust doing what they do under rare but not impossible circumstances. That should be our working hypothesis. Not because it's certain, but because it's where the evidence currently points. And if evidence shifts, forcing us toward more extraordinary explanations will follow it. That's the compact we make as scientists, but not yet. Not quite yet. Now we enter territory that makes most astronomers uncomfortable, where careers can be damaged by saying the wrong thing to the wrong journalist, where the line between legitimate scientific speculation and tabloid sensationalism becomes perilously thin. But we have to talk about it, because it's being talked about, and because, however unlikely, it represents a hypothesis that some serious scientists think deserves consideration. This is speculation. Let me be absolutely clear about that up front. What follows is not established science. It's a hypothesis that most researchers consider improbable, maybe even implausible. But improbable is not the same as impossible. And in science, we're supposed to follow evidence even toward uncomfortable conclusions. Abraham Loeb is not a fringe figure. He's a former chair of Harvard's astronomy department, a prolific researcher, a public intellectual who engages with media in ways most academics avoid.
He's known for bold hypotheses' willingness to entertain ideas his colleagues dismiss as too speculative. Oumuamua, that first confirmed interstellar visitor in 2017, became a vehicle for Loeb's techno-signature advocacy. He proposed it might be a light sail, an artificial structure pushed by radiation pressure, when most astronomers favored natural explanations. That Oumuamua episode divided the community. Some appreciated Loeb's willingness to think outside conventional bounds, his advocacy for considering techno-signatures seriously. Others cringed at what they saw as premature speculation, arguing that proposing alien artifacts without strong evidence undermines scientific credibility. Now 3i Atlas has become the next battleground. Loeb and collaborators have spoken and written about the possibility of controlled motion, a probe executing maneuvers. The media predictably amplified this angle.
Suddenly, 3i Atlas is being called potentially artificial in headlines, even though the scientific consensus leans strongly toward natural explanations. So, let's examine the engineered object hypothesis carefully. What would it actually claim? What evidence might support it? And why do most scientists remain skeptical? The hypothesis rests on timing and directionality. One interpretation suggests that if the sun-facing emission observed in July acted as braking thrust, pushing the object slightly toward the sun and therefore slowing its orbital motion, then the subsequent anti-solar tail could represent forward thrust, accelerating the object outward as it swings around perihelion. Such a maneuver would resemble trajectory correction, the kind of burn a spacecraft makes to fine-tune its path through space. Before dismissing this as wild speculation, consider what observational signatures would support it. First, sustained non-gravitational acceleration beyond what sublimation models predict. If the thrust continues longer than thermal models say, outgassing should last, or if the acceleration is larger than the mass loss rate, can explain that's an anomaly worth investigating. Second, repeatable reorientation of the jet axis. Natural comets can have multiple jets, but they're tied to the body's rotation and illumination pattern. It's worth considering whether jet direction changes that don't correlate with rotation or solar heating might indicate something unusual. Third, spectral anomalies. If the emitted material has composition inconsistent with typical cometary volatiles, that demands explanation. So far, none of these smoking gun signatures have been definitively detected, but the observations are incomplete. The object is faint, moving fast, difficult to track continuously. Gaps in the data mean we can't rule out brief episodes of unusual acceleration or spectral features that appeared when no telescope was watching. The absence of evidence is not evidence of absence, a phrase that applies here more than in most astronomical puzzles. Testing the engineered object hypothesis requires long-term astrometric monitoring. Astronomers need to measure the object's position precisely repeatedly over months and years. They then fit those positions to orbital models comparing purely gravitational trajectories to models that include non-gravitational terms. The residuals differences between predicted and observed positions reveal whether something beyond gravity is affecting the motion. Small random residuals are normal. Large systematic residuals indicating sustained thrust in a consistent direction would be extraordinary. Speculation aside, polarimetric observations could help too. Dust particles scatter light-producing polarization patterns that depend on grain size, shape, and composition. Natural cometary dust has characteristic polarization signatures. One hypothesis worth exploring is whether inconsistent polarization might suggest unusual materials. Another test involves trajectory analysis. Is the orbit of 3i Atlas special in any way? Does it approach the inner solar system at an angle or speed that seems too convenient, too carefully chosen? Interstellar objects have random trajectories determined by their ejection from their home systems and their path through the galaxy. Some researchers have suggested that if an orbit shows fine-tuning that raises eyebrows, it might warrant closer scrutiny. However, defining what constitutes suspicious fine-tuning is subjective. With a sample size of only 3 known interstellar visitors, we don't yet know what typical distributions should look like. The community's reaction to this hypothesis has been mixed, leaning toward skepticism. Most astronomers prefer mundane explanations until forced otherwise. The history of supposed anomalies that turned out to be natural is long. Pulsars were briefly thought to be alien beacons until neutron star physics explained them. Fast radio bursts generated exotic speculation until observations pinned them to astrophysical sources. The null hypothesis that 3i Atlas is a weird but natural comet carries strong prior probability. Yet Loeb and collaborators argue that dismissing the possibility without testing it is unscientific. Science advances by considering hypotheses, even uncomfortable ones, and designing observations to rule them in or out. The discovery of extraterrestrial technology would be monumental. So monumental that it justifies more scrutiny than we'd give most fringe ideas. The cost of false negatives, missing real technosignatures because we didn't look carefully enough, some argue might be higher than the cost of false positives. This debate touches on the sociology of science. How do researchers balance open-mindedness against the risk of being spectacularly wrong? How does the community handle claims that blur the line between legitimate inquiry and sensationalism? Loeb's prominence, his willingness to engage media, has amplified these questions. Some colleagues appreciate his advocacy for techno-signature research. Others worry that premature speculation undermines credibility. The risk-reward calculus is stark. If 3I Atlas is natural, which is vastly more likely, then this speculation eventually fades and we learn interesting comet science. If it's artificial, even if that probability's tiny, we're staring at the most consequential discovery in human history. That asymmetry, some argue, justifies serious follow-up. What would confirmation look like? You'd need multiple independent lines of evidence converging. Sustained acceleration inconsistent with outgassing. Spectral features implying manufactured materials, perhaps radio or infrared emissions at frequencies and modulation patterns that can't be explained by thermal processes. You'd need observations from multiple observatories' independent teams analyzing data, rigorous statistical analysis ruling out instrumental artifacts, and natural explanations. The standard for accepting such a claim would be and should be extraordinarily high. Proposed concepts include fast flyby probes launched on high-energy trajectories to intercept 3I Atlas after perihelion. Such missions would be expensive and technically challenging, requiring short development timelines to catch the object before it exits the solar system. The probability of approval through normal channels is essentially zero. By the time funding approval and construction happen, the object will be gone. Alternative approaches involve using existing assets. Ground-based telescopes can continue tracking. Space telescopes, if schedules allow, could provide higher resolution. Radio observatories could listen for transmissions. Even if 3I Atlas isn't deliberately broadcasting one hypothesis, suggests it might emit radio noise from charged particle interactions. The timeline matters. Perihelion on October 29th will subject the object to maximum heating and stress. If one considers the artificial hypothesis, the close solar passage might trigger systems that have been dormant during the cold approach. The weeks surrounding perihelion are the critical observation window. After that, 3I Atlas races back toward interstellar space, fading as distance from the sun increases. Eventually, it will be too faint for all but the largest telescopes to track. The engineered probe hypothesis feels like science fiction. And maybe it is. Maybe we're seeing patterns where none exist, projecting human notions of spacecraft maneuvers onto random ice sublimation. But the only way to know for certain is to gather more data test predictions and follow evidence wherever it leads. That's the scientific method, and it applies whether we're studying rock stars or things that might be neither. The honest assessment is this. The engineered object hypothesis remains on the table not because evidence supports it, but because evidence hasn't definitively ruled it out. That's a very different thing, and in science we're supposed to be honest about the difference.
What follows is clearly labeled speculation. We're exploring a thought experiment, not stating established facts. This represents the outer edge of scientific possibility, where evidence is thin, and imagination must be restrained by reason. Let's imagine just for a moment that 3I Atlas is not entirely natural, not a comet in the traditional sense, but something else, something that once had purpose. This hypothesis suggests we consider what observational signatures might distinguish an artificial object from a natural one. First, sustained non-gravitational acceleration without visible cause. Natural comets show acceleration from outgassing, but that acceleration is tied to observable activity. Brightness changes spectral emission dust production. Remove the activity and the acceleration stops. If one were to speculate, an artificial object might show thrust that continues even when no corresponding outgassing is visible.
Acceleration that persists too long or resumes after periods of dormancy in ways that thermal models can't explain. Has 3i Atlas shown this? Not definitively. But the observations are incomplete. Long gaps exist between measurement epochs. If there were brief burns during those gaps, we might not detect them unless we're monitoring continuously. Second spectral anomalies suggesting manufactured materials. Comets are made of primordial stuff, ices and dust left over from planetary system formation. They shouldn't contain processed metals or manufactured compounds. One could hypothesize that detecting emission lines from metallic species, unusual molecular complexes or materials inconsistent with natural cometary composition might indicate something artificial. Some reports have mentioned unusual spectral features, but data quality and interpretation remain contentious. Definitive high-resolution spectroscopy would settle this question.
Third, radio or infrared signatures inconsistent with thermal emission. Natural objects emit radiation according to their temperature. That thermal emission has a characteristic spectrum described by blackbody physics. Speculation sometimes considers whether deviations from that spectrum or narrowband radio emissions might indicate internal power sources or electronic systems. Even unintentional electromagnetic noise could be detectable if an object contains active electronics. No confirmed radio detections of 3i Atlas have been reported, but that doesn't mean searches have been comprehensive. Radio telescope time is precious, allocated to projects with clearer scientific payoffs than speculative SETI observations. Fourth, trajectory fine-tuning.
Is there anything special about 3i Atlas's orbit? Does it pass unusually close to the Sun or to Earth in ways that seem designed rather than random? The orbit does bring it relatively close to Earth in December, about 270 million kilometers at closest approach. That's not extremely close by astronomical standards, but it's close enough for detailed observations. Some have suggested considering whether this timing is coincidental or convenient. But with only 3 interstellar objects known, we lack baseline statistics to judge what constitutes suspicious geometry. Fifth, the pattern of the jet reversal itself. If one entertains the hypothesis, the timing around perihelion, the gradual nature of the transition, and the absence of corresponding orbital changes could be interpreted as indicators of control rather than passive sublimation. A braking burn as the object approaches reducing velocity. Then, at the optimal moment, a reversal to forward thrust using the Sun's gravity for a slingshot maneuver that flings the object back toward interstellar space on a precisely chosen trajectory. This interpretation requires assuming capabilities and intentions we have no evidence for. It's the weakest form of argument explaining one mystery by invoking a larger mystery. But the question persists. If you wanted to use another star system's sun as a gravitational slingshot, how would you do it? You'd need to adjust your trajectory as you approached, make small corrections, then accelerate outward at perihelion to maximize the energy gained from the close pass. That's exactly the pattern some interpretations suggest we're observing. Mission concepts to investigate 3i Atlas physically would face brutal constraints. The object is moving fast on a hyperbolic trajectory. After perihelion, it will race back out of the solar system at high velocity. Catching it requires enormous delta V, the change in velocity needed to match trajectories. Chemical rockets can't do it with reasonable mass. Nuclear propulsion might work, but isn't flight-ready. Solar or laser sails could build speed over time, but probably not fast enough. Proposed concepts include small probes launched on minimum time trajectories to intercept the object while still within a few AU of the Sun. These wouldn't rendezvous just zip past at high relative velocity snapping images and spectra during a brief encounter. Even that limited mission would require rapid development launch within months and significant funding. The probability of approval through normal channels is essentially zero. Alternative approaches involve long baseline observation rather than physical intercept. Continue tracking for years as it recedes. Monitor for behavior changes, radio emissions, trajectory adjustments. Deploy new assets optimized for faint object tracking in the outer solar system. The data might never be definitive, but accumulation of evidence over time could shift probabilities. If one imagines artificiality were confirmed, the implications cascade outward. First, we're not alone. That's been suspected, even assumed by many scientists based on the size and age of the universe, but knowing is different. Proof of extraterrestrial technology would be the most consequential discovery in human history. Second, interstellar travel is possible. If someone sent a probe across light years, the engineering challenges we consider nearly insurmountable have been solved. That suggests civilizations can persist long enough to develop such capabilities. Third, we'd have to reconsider previous anomalies. Was Oumuamua artificial too? Are there other objects in our catalogs that we dismissed as natural but deserve re-examination? Speculation extends to whether the galaxy might be full of such probes, a network of exploration left by multiple species. We might be seeing the trail markers of older civilizations. Fourth, implications for humanity's future. If others have achieved interstellar capability, we might too. The feasibility of star travel becomes less speculative, more engineering challenge. But let's be absolutely clear. The null hypothesis remains vastly more probable. 3I Atlas is almost certainly a natural comet with unusual but ultimately explicable behavior. The compositional transition model probably explains most or all observations. The engineered object hypothesis will likely fade as more data arrive, joining the long list of initially intriguing anomalies that resolve to mundane explanations. This speculation exists not because evidence demands it, but because the asymmetry of consequences justifies consideration. If natural, we learn interesting comet science. If artificial, everything changes. That asymmetry means even a tiny probability of artificiality might justify scrutiny beyond what we'd normally allocate to natural objects. But probability matters, and right now the probability strongly favors natural explanations. The honest position is we're watching carefully. Testing hypotheses, remaining open to surprises while expecting none. And if surprises come, we'll follow the data. That's the promise of science.
The clock is ticking louder now. Each day brings us closer to the moment that will either explain 3I Atlas or deepen its mystery into legend. Perihelion arrives on October 29, 2025 at approximately 11:36 UTC. The comet will reach its closest point to the Sun at 1.3526 astronomical units, about 203 million kilometers. That's well inside Earth's orbit, though not dramatically so, roughly the distance from the Sun to the middle of the asteroid belt. But that distance is close enough. Close enough for the Sun's radiation to intensify dramatically. Close enough to subject the nucleus to thermal stress that will test every ice reservoir, every structural weakness, every hidden property that the object carries. Perihelion is the crucible. Everything we've discussed, every model, every speculation, every measurement will be tested during the hours and days surrounding that closest approach. If the object contains volatiles, they'll sublimate furiously.
Surface temperatures will reach hundreds of Kelvin. Any water ice within meters of the surface will transition to steam, venting into space with explosive force. If structural weaknesses exist, cracks, voids, boundaries between strong and weak material, the thermal stress might trigger fragmentation. We've watched comets break apart at perihelion before. Dramatic disintegrations that reveal internal structure and composition in ways no spacecraft could. The observational challenges are considerable. Perihelion places 3i Atlas relatively close to the Sun as viewed from Earth. That means observations must be carefully timed to avoid the glare of our star and the bright sky of daytime. Ground-based telescopes have narrow windows before dawn or after dusk, when the comet is visible above the horizon, but the Sun is sufficiently below. These twilight observations are tricky. The sky is still relatively bright, drowning out faint objects. Atmospheric distortion is often worse near the horizon. Space telescopes have advantages. They're not limited by Earth's day-night cycle, but even they must contend with bright backgrounds and potential damage from pointing too close to the Sun. The Hubble Space Telescope operates under strict solar avoidance angles. It can't point within a certain zone around the Sun without risking damage to sensitive instruments. Scheduling observations of 3i Atlas requires careful planning to catch the object when it's far enough from the Sun in the sky to be safe. The Nordic Optical Telescope and other ground facilities face similar but different constraints tied to twilight and seasonal viewing windows. Then there was the Mars flyby on October 3rd. On that date, 3i Atlas passed within about 30 million kilometers of the red planet. That's close by planetary standards, about a fifth of the distance from Earth to the Sun. Did Mars orbiters capture images? The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express were potentially positioned to observe. These spacecraft carry cameras designed for photographing the Martian surface, but they can be redirected to look at passing comets. ESA has confirmed that both orbiters attempted observations. Early reports indicate ExoMars TGO's Cassis camera captured images showing the comet's coma. The viewing angle from Mars was completely different than from Earth, providing a valuable independent perspective that helps break geometric degeneracies. What about high-resolution observations NASA's Mars Reconnaissance Orbiter carries? HiRISE, a camera capable of incredible detail. If HiRISE imaged 3i Atlas, those pictures could reveal structure invisible from Earth-based telescopes. But Mars orbiter time is precious, allocated months in advance for surface science. Whether anyone secured approval to target this fast-moving interstellar visitor remains to be seen. Data analysis is ongoing. The real payoff comes after perihelion. As 3i Atlas swings back outward, its brightness will initially remain high due to fresh outgassing triggered by solar heating. This is when astrometric precision matters most. Measure the object's position every few days. Track how its motion deviates from the pre-perihelion orbit. If non-gravitational acceleration suddenly appears or changes magnitude, that tells you something happened during or because of the perihelion passage. December 19, 2025 marks another critical date, Earth closest approach. At approximately 1.80 AU, about 270 million kilometers, the comet will be at its nearest to our planet. That's still far, but close enough for detailed observations. Large ground-based telescopes can capture high-resolution images and spectra. The James Webb Space Telescope, if its schedule permits, could provide infrared spectroscopy revealing composition details invisible at optical wavelengths. Spectral lines of water, carbon dioxide, carbon monoxide, methane, ammonia. All the common cometary volatiles, plus any exotic species, would appear in JWST's data. This is the best chance for definitive compositional characterization. The timeline also includes blackout periods when observations are difficult or impossible. Solar conjunction, when the comet appears too close to the Sun from Earth's perspective, creates gaps in coverage. During conjunction, optical telescopes can't safely point in that direction. Even radio communication can be difficult. Solar interference drowns out faint signals. 3i Atlas will pass through conjunction phases as its orbit carries it across our line of sight to the Sun.
Those gaps mean we might miss brief events, transient brightening, or morphology changes that appear and fade while no one is watching. Brightness evolution adds another layer of uncertainty. As the comet moves away from the sun post-perihelion, it will fade. The rate of fading depends on how active it remains. If outgassing shuts down quickly, volatiles, exhausted or surface-crusted, over brightness drops rapidly. Soon, the object becomes too faint for all but the largest telescopes. If activity persists, driven by subsurface heat retained from perihelion or delayed volatile release, the comet could remain observable longer. Historical comets show enormous variation. Some fade into obscurity within weeks. Others stay active for months. Coordination among observatories will be essential. Transient alert networks originally designed for supernovae and other astrophysical events can be adapted to track 3i Atlas.
When one telescope detects a sudden change, alerts go out to others, triggering follow-up observations. This multi-facility coordination has become standard in time-domain astronomy. Spectroscopic capacity is the bottleneck. Taking a spectrum requires concentrating the object's faint light and dispersing it across a detector. That process takes time and reduces signal compared to direct imaging. For a faint, fast-moving target, you need a large telescope, good tracking, and long integration times. Few facilities can do this on demand. Public interest adds another dimension. 3i Atlas has captured attention beyond usual astronomy circles. News articles, social media discussions, even government agencies asking questions. That attention can help secure telescope time and funding, but it also creates pressure. Astronomers must balance careful science against demands for quick answers. By December 19th, we'll have months of post-perihelion data. The trajectory will be precisely measured. Spectroscopy will have characterized composition changes. High-resolution imaging will have documented morphological evolution. The combination of all these data streams will either converge on a coherent natural explanation or leave us with residual anomalies that can't be easily dismissed. That convergence or lack thereof determines what happens next. If data confirm the compositional model, if everything fits the carbon dioxide to water transition narrative, then 3i Atlas becomes a fascinating but ultimately understood interstellar comet. Papers get published. Conferences hold sessions. Science moves forward slightly richer for the experience. If anomalies persist, if non-gravitational acceleration doesn't match sublimation models, if spectral features remain unexplained, then the conversation changes. Mission proposals get serious consideration. Observation campaigns extend beyond December. Perhaps international collaboration brings more resources to bear. The object hasn't left the solar system yet. At its current trajectory, it will take years to recede beyond Saturn's orbit. It will be very faint by then, but if the stakes are high enough, the investment in continued monitoring becomes justified. The next few months are a countdown, not just to perihelion and Earth approach, but to a decision point in how we think about interstellar space. The clock is ticking. By the time winter solstice arrives, we'll know far more than we do today. Something else is happening while 3i Atlas plunges toward the sun, something that changes the game entirely for the next interstellar visitor. We're building a new kind of observatory, not one telescope, but a system, a network of instruments that will transform our ability to detect, track, and characterize objects that move through our cosmic neighborhood. The Vera Rubin Observatory, formerly known as the Large Synoptic Survey Telescope, achieved first light in late 2025. This facility, situated on Cerro Pachón in Chile, represents a revolution in how we watch the skies. Rubin's design is purpose-built for wide-field surveying. Its 8.4-meter mirror isn't particularly large by modern standards, but paired with an enormous 3.2 gigapixel camera, the largest digital camera ever constructed for astronomy, it can image areas of sky the size of 40 full moons in a single exposure. More importantly, Rubin will repeatedly scan the entire visible sky every few nights, creating a time-lapse movie of the universe. When you compare images taken days apart, anything that moved or changed pops out immediately. Asteroids reveal themselves by shifting position. Supernovae appear as new bright points. And comets, including interstellar ones, show up as fuzzy moving objects, distinct from background stars and galaxies. The statistical implications are profound. Right now, we've confirmed only 3 interstellar objects, 3 over 8 years. The sample is too small to draw any conclusions about the population. Are interstellar comets common or rare? What fraction are active? Do they have unusual compositions reflecting different formation environments around other stars? We simply don't know. Rubin will answer these questions by discovering interstellar visitors at much higher rates. Projections suggest dozens per year once the legacy survey of space and time reaches full operation. That abundance transforms interstellar object science from anecdotal case studies to statistical analysis. You can compare distributions of orbits, compositions, activity levels. Outliers like 3I Atlas, if they exist, will become apparent against the background of normal interstellar comets. Early warning is another game changer. 3I Atlas was discovered relatively late in its approach, giving limited time for follow-up before Perihelion. Future interstellar visitors detected by Rubin will be caught earlier, perhaps years before Perihelion. That means extended monitoring campaigns, watching how activity evolves over a larger range of heliocentric distances, constraining models more tightly than snapshots at just a few epochs allow. The survey will also create archival data. Every patch of sky gets imaged multiple times across multiple filters over years. That archive can be searched retroactively. When a new interstellar object is discovered, astronomers can look back through the archive to see if it appeared in earlier images before anyone recognized it. Those pre-discovery detections extend the observational baseline, improving orbit determination and activity history. For 3I Atlas specifically, Rubin came online too late. But imagine if Rubin had been operating since 2023. The object might have been detected at 5 or 6 astronomical units visible but faint. Early spectroscopy could have characterized composition before major activity began. The entire evolution from dormant to active to jet reversal would have been documented continuously rather than pieced together from sparse observations. This raises a tantalizing question. How many objects like 3I Atlas have passed through the inner solar system undetected? We've only been systematically searching for interstellar visitors for a few years. Before that, any object on a hyperbolic orbit might have been noticed, but not recognized as interstellar. Rubin changes the detection threshold dramatically. Its sensitivity and cadence mean fainter, smaller objects become discoverable. The population we sample shifts toward lower masses, potentially revealing different demographics than the few large visitors we've found so far. The data volume is staggering. Rubin will generate tens of terabytes per night, requiring sophisticated automated pipelines to process images, detect transients, and issue alerts. Machine learning algorithms will classify detections separating asteroids from comets, from supernovae, from variable stars. The stream of alerts, potentially millions per night, feeds into follow-up networks, where human observers decide what deserves deeper investigation. For interstellar objects, the signature is distinct but subtle. Hyperbolic orbits with high eccentricity separate them from bound solar system objects.
But measuring orbit requires multiple detections over time. A single detection can't distinguish interstellar from an as-yet poorly determined asteroidal orbit. Automated pipelines must track moving objects across multiple nights, fitting orbits and flagging those with parameters suggesting extrasolar origin. Now add another new instrument to the mix, the foremost multi-object spectroscopic telescope, which also achieved first light in late 2025 at the European Southern Observatory's Perihelion facility. Foremost doesn't have its own mirror. It piggybacks on one of the very large telescope's four 8.2-meter telescopes. But what it brings is spectroscopic firepower on an industrial scale. Most spectrographs can only observe one object at a time, maybe a handful if you're lucky. For most can capture spectra from 2,400 objects simultaneously. It works using fiber positioning robots, 2,400 tiny mechanical arms, each independently aiming a fiber optic cable at a different target in the telescope's field of view. The field of view covers roughly 4 square degrees of sky. This isn't just a new tool, it's a new category of tool. For small body science, the bottleneck has never been finding objects, it's understanding them. Rubin will discover tens of thousands of new moving targets every night, but discovery without characterization is just a list of coordinates. You need spectra to know what something actually is. What's it made of? Is it rocky or icy? Does it have organic molecules? Is it outgassing? Foremost's ability to simultaneously observe thousands of targets means it can conduct massive surveys of asteroids and comets, building libraries of spectral data that help us classify objects faster when new ones appear. It can study the background population, the ordinary residents of the solar system, giving us the baseline we need to recognize when something extraordinary shows up. If an interstellar object appears, if something like 3I Atlas gets confirmed and needs immediate follow-up, Foremost can be part of a coordinated response that doesn't require abandoning other scientific programs. It can take spectra of thousands of comparison objects while other instruments focus on the target itself. It makes rapid response spectroscopy feasible in ways that simply weren't possible before. Now imagine if these instruments had been operational when Oumuamua passed through. We could have caught it earlier, tracked it longer, characterized its composition. We might have answers instead of arguments. For 3I Atlas, we're in a transitional moment. Rubin and Foremost came online too late to catch the early approach, but they'll be ready for post-perihelion monitoring. And they'll be fully operational for the next interstellar visitor. The synergy is remarkable. Rubin finds them early and tracks them precisely. Foremost characterizes them spectroscopically at scale. JWST provides infrared composition details. Ground-based high-resolution imaging documents morphology. We're assembling a toolkit without quite knowing what we're building it for. Only now, as visitors arrive, are we realizing what we've created. A system for detecting and characterizing the rare, the unusual, the objects that pass through from elsewhere. The timing almost feels intentional. 3 interstellar objects in 8 years, and suddenly we're deploying instruments perfectly suited to studying exactly these phenomena. Coincidence? Probably. The universe doesn't plan ahead for our convenience, but it's a fortunate coincidence, because the next visitor will find us far better prepared than we were for Oumuamua, better prepared than we are now for 3I Atlas. Whether that preparation helps us understand natural phenomena better or reveals something we're not ready to comprehend, well, we'll find out soon enough. The desert supercomputers are waking up, the sensors are coming online, the network is forming, and the next chapter of this story is about to be written. While we watch 3I Atlas, other dramas unfold across the solar system and beyond. Stories that seem unrelated but share common threads of uncertainty, ambition, and the human drive to explore what we don't understand. NASA announced in late 2025 that it's reopening competition for the Artemis lunar lander beyond the original single contract award to SpaceX. That award designated SpaceX's Starship as the system that would carry astronauts from lunar orbit down to the surface. Starship is an enormous rocket still in development, promising unprecedented capability, but facing repeated delays and technical challenges. The decision to reopen competition reflects both practical concerns and political pressures. Relying on a single contractor carries risk. If Starship development encounters insurmountable problems, the entire Artemis schedule collapses. Having a backup option provides insurance. It also fosters competition, theoretically driving innovation and cost control.
The parallel to Three-Eye Atlas is subtle but real. Both situations involve operating under uncertainty with incomplete information and high stakes. NASA must decide how much schedule margin to build, in how much redundancy to pay for how much risk to accept. Too conservative and the program becomes prohibitively expensive, losing political support. Too aggressive and technical failures undermine credibility. Astronomers face similar trade-offs with Three-Eye Atlas. Allocate too much telescope time and you shortchange other science. Too little and you might miss the observation that clinches the case. Resources are finite. Choices have consequences. The decision calculus mixes technical assessment with intuition about where high-value opportunities lie. Meanwhile, the James Webb Space Telescope continues making discoveries that showcase its extraordinary capabilities. Recent announcements include detection of atmospheric signatures on ultra-hot rocky exoplanets, worlds so close to their stars that their surfaces are molten. JWST's spectroscopic instruments detected signatures of vaporized minerals in these planets' atmospheres, confirming theoretical predictions about lava worlds. The technical achievement is remarkable. The planet is hundreds of light years away, a tiny point lost in its star's glare. JWST observes during transits when the planet passes in front of its star from our view. Starlight filtering through the planet's atmosphere carries spectral signatures that JWST can detect. This transmission spectroscopy technique is one of JWST's strengths. Now consider how similar techniques apply to comets. A comet's coma contains molecules that emit and absorb at infrared wavelengths. Water vapor, carbon dioxide, carbon monoxide, all accessible to JWST. For Three-Eye Atlas, such observations would be invaluable. Optical spectroscopy has provided clues, but infrared is better for quantifying volatiles. JWST could measure isotopic ratios that reflect formation conditions, encoding information about the temperature and chemistry where the comet condensed billions of years ago in another star system. The lava world discovery also demonstrates JWST's sensitivity to unusual chemistry. Vaporized silicates in an atmosphere are exotic by Earth standards, but natural given extreme conditions. Similarly, if Three-Eye Atlas exhibited unusual spectral features, JWST could characterize them precisely. That precision matters when evaluating hypotheses. Definitive spectroscopy provides evidence or rules out claims conclusively. Elsewhere, the LIGO Gravitational Wave Observatory continues its observing run, detecting ripples in spacetime from colliding black holes and neutron stars. When LIGO detects a signal, alerts go out within seconds to telescopes worldwide. Those telescopes search for electromagnetic counterparts, optical X-ray or radio emissions from the same event. This multi-messenger astronomy, combining gravitational and electromagnetic observations, provides far richer information than either alone. The coordination required is intense. LIGO can only localize events to large patches of sky, sometimes hundreds of square degrees. Follow-up telescopes must search that entire region quickly before any transient fades. This model directly parallels what's needed for interstellar object follow-up. Discovery alerts trigger cascades of confirmatory observations, orbit determination characterization. The community has developed protocols learned from gravitational wave campaigns about how to coordinate efficiently. One lesson: the value of rapid response infrastructure. Having telescopes on standby queued to interrupt for targets of opportunity enables immediate follow-up. Manual scheduling takes days. Automated triggers reduce that to hours or minutes. Another lesson: data sharing. Gravitational wave events are public immediately. Anyone can access alerts and participate in follow-up. That openness accelerates discovery because more observers mean better sky coverage. The model contrasts with older approaches where discoverers held data proprietary until publication. Open data policies, now standard in many fields, trace partly to gravitational wave astronomy's success. These parallel stories, Artemis JWST LIGO, illustrate shared challenges: resource allocation, rapid response, false positives, coordinating large teams across institutions and nations. Technology development links these fields. Advances in detectors, data analysis, mission planning cross-pollinate. An algorithm developed for gravitational waves might apply to exoplanet searches or asteroid tracking. The community building deserves attention too.
Gravitational wave astronomy required convincing diverse groups to collaborate, sharing resources and credit. That didn't happen spontaneously. It required leadership, clear governance incentives structured to reward teamwork. For 3i Atlas, no formal collaboration exists comparable to LIGO. Observers self-organize, coordinating informally. That works for small campaigns, but might not scale as interstellar object science grows. The philosophical connection is the quest to observe rare, transient phenomena that reveal fundamental truths. Gravitational waves come from the most extreme environments where gravity is strongest. Interstellar comets sample conditions in other solar systems. Both push boundaries of what we can learn about the universe. Both drive public engagement. People follow breaking news about newly detected events, curious what each discovery reveals. The synergy between different branches of astronomy is growing. Techniques developed for one apply to others. Data from multiple fields inform broader questions about formation chemistry, the potential for life. 3i Atlas sits at an intersection of these interests. An interstellar visitor carrying information about its home system while passing through ours. Whether we extract that information depends on resources, priority, and coordination across the global astronomical community. But the tools exist. The infrastructure is forming. The lessons are being learned, and when the next crisis or opportunity emerges, we'll be better prepared than we were before. That's progress. Slow, uneven, frustrating progress. But progress nonetheless.
Let's talk about the most likely outcome. The one where nature surprises us but doesn't overturn everything we know. If the compositional model is confirmed by post-perihelion observations, if spectroscopy reveals the predicted transition from carbon dioxide to water ice, if high-resolution imaging shows complex but natural surface features, then 3i Atlas becomes a case study. Fascinating, certainly, but ultimately explicable. This is the comfortable universe, the one where physics works as expected, where strange appearances resolve to understood phenomena once enough data accumulate. In this scenario, papers get published in prestigious journals. Compositional stratification in interstellar comet, 3i Atlas evidence for formation in a cold outer disk environment. The abstract would describe observations compared to models conclude that the jet reversal resulted from evolving volatile activity as predicted by thermal and compositional gradients. Conferences would hold sessions. Researchers would present posters showing spectroscopic time series, photometric light curves, astrometric residuals. Graduate students would write dissertations analyzing the data. 3i Atlas would be added to the growing catalog of interstellar visitors, a data point in studies of galactic small body populations. It would inform models of planetary system formation, volatile retention during interstellar travel, and cometary activity mechanisms. We'd learn that interstellar comets can be compositionally stratified in extreme ways, that carbon dioxide dominance in outer layers creates unusual early activity, that transitions between volatile regimes can happen rapidly enough to create apparent reversals in emission direction. These lessons would be valuable. They'd expand the known range of cometary behavior. They'd help us interpret future interstellar visitors more quickly, recognizing similar patterns. The next comet showing sun-facing emission wouldn't trigger speculation.
We'd check its heliocentric distance, run compositional models, and probably conclude Another CO2-rich interstellar comet transitioning to water ice. Expected behavior given formation conditions. In this comfortable universe, Loeb's artificial object hypothesis fades like so many bold speculations before it. Remembered as an interesting idea that failed when tested, used in classrooms as an example of how extraordinary claims require extraordinary evidence. Oumuamua would be reinterpreted too. Maybe its unusual acceleration came from similar compositional effects. Maybe we missed the outgassing because our instruments weren't sensitive enough. The broader implication: interstellar objects are diverse. They sample formation conditions around other stars, and those conditions vary. Some stars have colder outer disks, creating CO2-rich comets. Others produce icy bodies more like solar system counterparts.
Statistical analysis of dozens of interstellar visitors detected by Rubin would reveal patterns. Compositions correlate with stellar type. Activity levels reflect formation distance. Orbits show clustering from nearby stellar nurseries or random distribution from the general galactic population. This is what normal scientific progress looks like. Slow accumulation of data, refinement of models, expansion of knowledge. No paradigm shifts, no revolutions. Just the patient work of understanding nature in greater detail. And honestly, this is what we should expect. The universe is under no obligation to be exotic on human timescales. Most phenomena, when examined carefully, have mundane explanations. That's not disappointing, it's how science works. Every explained mystery makes the next one approachable. Every model that holds up under testing gives us confidence to extend it further. The comfortable universe is the one where we're slowly, steadily learning.
Where each interstellar visitor teaches us something new about planetary system diversity without overturning foundational physics. In this universe, 3I Atlas is a wonderful natural experiment. A comet from another star system carrying volatile ices that formed around a different sun, arriving just as we developed the instruments to study it properly. The jet reversal, elegant physics, carbon dioxide sublimation giving way to water ice with optical properties that made the transition dramatic when viewed from Earth's changing vantage point. The timing, coincidence. Objects don't plan their perihelion approaches to coincide with our observing campaigns. The mass discrepancy resolved by better estimates of nucleus size and density. Turns out it's larger than initial calculations suggested, or outgassing is more symmetric than single viewing angle observations revealed. Every anomaly, when examined closely, has a natural explanation.
Not always the first explanation we thought of, and not always simple, but natural, within the bounds of known physics. This is the story most scientists expect to tell in 6 months after perihelion data have been analyzed and follow-up observations have filled gaps in our understanding. It's the story that preserves the continuity of our knowledge. Ice is ice. Comets are comets. Interstellar space is cold and hostile, but the objects that traverse it follow the same physical laws as everything else. And if this is the story we end up telling, that's okay. That's good. That's science working exactly as it should. We saw something unusual. We investigated carefully. We ruled out exotic explanations, not because we're closed-minded, but because data didn't support them. We explained the phenomenon using extensions of known physics. We learned something new about the diversity of cometary behavior. We added to humanity's collective understanding of the cosmos. That's a success.
That's why we do this work. The comfortable universe isn't boring. It's vast and ancient and full of wonders we're only beginning to map. Every star system is an experiment in planet formation. Every interstellar visitor is a messenger carrying news from places we'll never visit in our lifetimes. 3I Atlas. In this telling is one more messenger. Its message: comets from cold outer disks behave like this. Compositions stratify this way. Activity evolves along these patterns. Valuable information. Worth the telescope time, the analysis effort, the public interest it generated. And when the next visitor arrives, we'll be better prepared.
We'll know more about what to look for, how to interpret observations, what questions to ask. That's the comfortable universe. And most likely that's where we're living. Now let's walk through the thought experiment. The unlikely scenario, the one that would change everything. This is clearly speculation, a thought experiment about consequences, not a claim about what's actually happening. Imagine it's March 2026. Spring is arriving in the northern hemisphere. 3i Atlas has rounded the sun and is heading back toward interstellar space. 6 months of post-perihelion observations have accumulated. Multiple independent teams have analyzed the data, and slowly, reluctantly, consensus is building toward an impossible conclusion. In this scenario, sustained non-gravitational acceleration has been detected that sublimation models cannot explain. The thrust continues long after thermal models say volatiles should be depleted. The acceleration shows directional changes uncorrelated with solar heating or rotation. Spectroscopy has revealed anomalies, emission features that don't match any known cometary molecule, possibly metallic absorption lines suggesting processed materials, ratios of isotopes inconsistent with natural nucleosynthesis. Radio observations detected narrowband signals, nothing obviously artificial, no prime numbers or mathematical sequences, but electromagnetic emissions at frequencies that thermal processes can't produce. The orbital solution has been refined to extraordinary precision, and the trajectory shows fine-tuning that strains credibility. The perihelion distance, the timing, the exit vector all seem optimized in ways that random galactic dynamics shouldn't produce. Multiple papers have been published, each carefully worded. Unexplained non-gravitational acceleration in interstellar object 3i Atlas. Unusual spectroscopic signatures warrant further investigation. Radio emission inconsistent with thermal models. No single paper claims artificiality, but collectively they're building a case that can't be ignored. The media has picked up on it. Headlines scream, "Scientists can't explain interstellar visitor." Is 3i Atlas an alien probe, comet or spacecraft? The mystery deepens. In this thought experiment, astronomical organizations convene emergency meetings. The International Astronomical Union forms a special committee. NASA and ESA coordinate analysis efforts. Intelligence agencies quietly start asking questions. The standard for accepting artificiality must be extraordinarily high. 5 sigma statistical significance, the same threshold used for major physics discoveries. Multiple independent observations ruling out all natural explanations. Peer review by adversarial teams specifically tasked with finding flaws. But in this scenario, that standard is met. Slowly, painfully, with enormous controversy and debate, the evidence accumulates past the point where dismissal becomes untenable. And then comes the announcement.
Carefully worded, hedged with caveats, but unambiguous in its core claim, we have detected signatures in 3i Atlas that are inconsistent with all known natural processes. The possibility that this object is of artificial origin must be seriously considered. What would follow? First, media frenzy. The story would dominate news cycles for weeks. Every detail analyzed, debated, sensationalized. Social media would explode with theories ranging from scientific to absurd. Second, geopolitical activation. The United Nations Office for Outer Space Affairs would suddenly matter. Treaties about extraterrestrial contact, mostly theoretical until now, would be dusted off and examined. Which nation or institution gets credit? What are the security implications should information be classified or shared openly? These questions would have no clear answers and enormous consequences. Third, scientific mobilization. Every major observatory would want follow-up time.
Mission proposals to intercept the object would multiply. Funding that seemed impossible suddenly becomes available. But there's a catch. By the time this confirmation happened in March 2026, 3i Atlas would be receding rapidly. Already faint, getting fainter. The window for detailed observation closing. Emergency mission concepts would face brutal physics. Chemical propulsion can't catch it. Nuclear propulsion isn't ready. Solar sails need years to build velocity. The best option might be do nothing. Keep watching as long as possible, learn what we can, and prepare for the next one. Because if 3I Atlas is artificial, it's probably not alone. The galaxy might be full of such probes. We've detected 3 interstellar objects in 8 years. How many others passed through undetected before we were looking forth philosophical upheaval? We're not alone. That statement, suspected by many, believed by some, would become established fact.
Every religion, every philosophy, every framework for understanding humanity's place in the cosmos would need to adjust. Some worldviews would adapt easily. Others would face existential challenges. Fifth, implications for humanity's future. If another civilization achieved interstellar capability, we might too. Feasibility questions shift from if to how and when. Funding for propulsion research would increase. Projects like Breakthrough Starshot, currently speculative, would receive serious backing. Space agencies would refocus priorities toward interstellar preparedness. Sixth, re-examination of past anomalies. Was Oumuamua artificial too? What about anomalous signals in archival data? How many other objects did we miss or misidentify? A systematic search through decades of astronomical observations would begin. Machine learning algorithms trained to spot techno-signatures would comb through archives. Some fraction of false positives is inevitable. Ordinary objects reinterpreted as possible artifacts. The challenge would be maintaining scientific standards while investigating seriously. Seventh, the question of intent. If 3I Atlas is artificial, why is it here? Was it sent deliberately to this star system? Is it a probe exploring random stars? Is it ancient, built by a civilization long extinct? Does it still have purpose, or is it derelict? The object shows no signs of communication, no response to radio signals we've transmitted, no variation in behavior suggesting awareness of our observation. Maybe it's not designed to communicate. Maybe it's pure science mission gathering data about stellar systems and transmitting results to somewhere. Or maybe it's dead, failed millennia ago, tumbling through space with just enough operational capacity to execute basic trajectory corrections, but no higher functions remaining. We wouldn't know, not without intercepting it. Not without getting close enough to see structure probe surfaces detect energy signatures beyond what telescopes can resolve. And that's not happening with current technology. Not in time, not before it leaves. This scenario confirmation of artificiality remains highly improbable. The vast majority of scientists consider it nearly impossible that 3I Atlas is artificial. But the thought experiment is valuable. It clarifies what evidence would be required, what observations to prioritize, what infrastructure we'd need to respond effectively, and it highlights the asymmetry. If natural, we learn comet science. If artificial, everything changes. That asymmetry justifies taking the question seriously, even if the probability is tiny. Missing genuine evidence of extraterrestrial technology because we didn't look carefully enough would be a failure of historic proportions. So we watch. We measure, we test, we remain skeptical but thorough. And if the impossible happens, if evidence truly points toward artificiality, we'll follow it. Because that's what science demands. Follow the data wherever it leads, no matter how uncomfortable the destination. But again, this is speculation. The overwhelmingly most likely outcome is that 3I Atlas is natural. And 6 months from now, we'll tell a very different story about ice physics and compositional diversity. The thought experiment exists not because we expect it to happen, but because considering possibilities, however remote, is part of thorough investigation. And because the question, what if, is one of the most powerful questions humans can ask. Let's return to something that actually happened, something concrete, observable, real.
On October 3, 2025, 3i Atlas passed within approximately 30 million kilometers of Mars. That's about 1/5 the distance from Earth to the Sun, close by planetary standards. Mars had a front-row seat to something Earth-based observers struggled to see clearly. A completely different viewing angle unencumbered by Earth's atmosphere or daylight constraints. The European Space Agency's ExoMars Trace Gas Orbiter and Mars Express spacecraft were positioned to observe. These orbiters weren't designed for comet watching, they're studying Mars. But their cameras can be redirected. Priorities can shift when opportunities arise. ESA confirmed both orbiters' attempted observations. ExoMars TGO's CASIS camera, the color and stereo surface imaging system, captured a series of images showing 3i Atlas as a slightly fuzzy white dot moving against the background stars. The comet was incredibly faint from Mars's perspective, roughly 10,000 to 100,000 times dimmer than the Martian surface the cameras normally photograph. Imaging it required long exposures and careful planning. CASIS couldn't distinguish the nucleus from the coma. At 30 million kilometers, resolving a nucleus a few kilometers across would be like seeing a mobile phone on the moon from Earth, impossible with current technology. But the coma was visible. A few thousand kilometers across, created as solar heating, causes the comet to release gas and dust. The coma appeared as a diffuse glow brightness decreasing rapidly with distance from the center. No tail was visible in the initial CASIS images. Tails are much dimmer than comae, and the exposure times weren't long enough to capture such faint features. But future analysis stacking multiple images together might reveal more.
Mars Express also attempted observations with its visual monitoring camera, though these were taken with shorter exposure times, only half a second compared to CASIS's 5 seconds. The shorter exposures make detection more difficult. Scientists continue analyzing the Mars data. The value isn't just in what the images show directly, but in what they allow us to calculate. From Mars's vantage point, the viewing geometry was completely different than from Earth. The scattering angle, the angle between incoming sunlight, the dust particles, and the observer, determines how bright dust appears. Different scattering angles reveal different populations of particles. Forward scattering, where sunlight passes through dust before reaching the observer, preferentially highlights small particles. Back scattering emphasizes larger grains. By combining Earth-based observations with Mars, observations taken simultaneously, astronomers can triangulate.
They can separate effects of viewing geometry from intrinsic changes in the comet's activity. If the anti-tail observed from Earth in July appeared different from Mars's viewing angle that constrains particle size distributions and ejection velocities. If Mars and Earth saw similar features despite different perspectives, that suggests the emission pattern was genuinely unusual rather than a projection artifact. The Mars flyby also tested something else. How close could instruments get while still functioning? ESA's orbiters were well beyond any danger. 30 million kilometers is an enormous safety margin. But if 3i Atlas were emitting anything beyond visible light and dust, the orbiters might have detected it. Mars Express carries spectrometers, Omega and SpyCam, designed to study the Martian atmosphere. Could they detect gases from 3i Atlas? Unlikely at that distance, but attempts were made. ExoMars TGO's Nomad spectrometer, which normally studies trace gases in Mars's atmosphere, also attempted observations. Any detection of cometary volatiles would be extraordinary given the distance and dilution of the coma. Results from these spectrometric observations haven't been publicly released yet. Analysis is ongoing. Data quality assessment is complex, and scientists are cautious about announcing findings before rigorous verification. But the attempt matters. It shows the astronomical community taking 3i Atlas seriously, coordinating assets across different space agencies, different missions, different planets to gather as much data as possible. There's poetry in it too. Mars, the red planet, watching an interstellar visitor pass by. Two travelers, both far from their origins, briefly sharing cosmic space. Mars formed 4.5 billion years ago in our solar system's protoplanetary disk. 3I Atlas formed around another star in conditions we can only infer. They're meeting now for the first and probably last time ships passing in the vast night. What did Mars see? A fuzzy blob moving against stars, unremarkable in appearance, distinguished only by its motion and the knowledge of what it represents. From Mars's perspective, 3I Atlas wasn't mysterious or controversial. It was just another comet, slightly unusual in trajectory, but fundamentally similar to thousands of others that have passed through the inner solar system. Mars doesn't speculate about artificial objects or techno-signatures. Mars doesn't debate compositional models or projection effects. Mars just exists, its instruments recording what's there, without interpretation, without expectation. There's something clarifying about that, about stepping outside our earthbound perspective literally and viewing the situation from another vantage point. The data from Mars won't solve all our questions about 3I Atlas, but it will help. Every observation, every viewing angle, every wavelength adds to the composite picture we're building. And in that patient accumulation of data, truth emerges. Not all at once, not with fanfare, but gradually, like stars appearing as twilight deepens into night. Mars asked its questions simply by watching, by being there, by pointing cameras at the right patch of sky at the right moment. The answer it provides will be partial, incomplete, requiring interpretation and integration with other observations. That's always how it works. No single measurement tells the whole story. But combined with everything else, Hubble's images, Nordic Optical Telescope's monitoring, JWST's spectroscopy, ground-based astrometry. Mars's contribution adds depth, literally adds another dimension to our understanding. Sometimes you need to be somewhere else to see clearly. Sometimes the most valuable perspective is the one that reminds you how limited your usual viewpoint is. Mars watched, Mars recorded. And in doing so, Mars participated in one of humanity's more interesting scientific investigations. Even if from Mars's perspective, it was just another day. We've come a long way together tonight, through compositional models and projection effects, through mass calculations and hypotheses ranging from conservative to extraordinary. Now it's time to separate what we know from what we suspect, to distinguish fact from interpretation, to acknowledge uncertainty while celebrating what we've learned. Here's what we know for certain. 3I Atlas was discovered on July 1, 2025 by the Atlas telescope in Chile. Its velocity and trajectory confirm it originated from outside our solar system, the third such object ever detected. The Hubble Space Telescope captured images in July showing unusual forward-directed emission. The Nordic Optical Telescope documented a gradual transition through September as this forward emission faded and a classical anti-solar tail grew. JWST spectroscopy detected extraordinarily high carbon dioxide levels in the comet's coma, among the highest CO2 to water ratios ever recorded. The object has lost approximately 2 million metric tons of material between July and October. Despite this substantial mass loss, no significant orbital perturbations have been detected. The best estimates place the nucleus mass at roughly 33 billion metric tons, suggesting a body several kilometers across. Uncertainty ranges are large, but the order of magnitude is solid. 3I Atlas reached perihelion on October 29, 2025, at 1.356 AU from the Sun. Earth's closest approach occurred on December 19 at 180 AU. Multiple observatories contributed data: Hubble, JWST, Nordic Optical Telescope, potentially Mars orbiters, and various ground-based facilities worldwide. These are facts, observations, measurements. They're not in dispute. Now, what remains uncertain? Why did the emission pattern reverse? The compositional transition model offers a compelling explanation, but it hasn't been definitively confirmed.
Alternative explanations involving projection effects, unusual outgassing patterns, or fragmentation remain possible. What's the precise composition? We know CO2 is abundant, but detailed molecular inventories, isotopic ratios, and dust properties are still being refined. What's the exact mass and size? Current estimates have large error bars. Better constraints require either closer observations or longer-term astrometric monitoring to detect subtle orbital perturbations. Is there anything genuinely anomalous, or will everything resolve to natural, if unusual, comet behavior once all data are analyzed? The uncertainty persists for several reasons. First, the object is faint and distant. Spectroscopy at high resolution is challenging. Many desired observations simply weren't possible with available resources and time constraints. Second, interstellar objects are new territory. We have only 3 confirmed examples.
Our understanding of their population properties, diversity, and typical behaviors is still developing. Third, observations were reactive rather than planned. Unlike a periodic comet whose return we can predict and prepare for, 3I Atlas appeared suddenly. The astronomical community scrambled to gather data, but gaps inevitably exist. Fourth, complex systems are complex. Even for well-studied solar system comets, predicting behavior is difficult. Outgassing depends on composition, structure, rotation, thermal history variables we can't measure directly. Looking ahead, post-perihelion monitoring will continue through the end of 2025 and into 2026. As long as the object remains bright enough, telescopes will track it. If activity increases dramatically after perihelion, as often happens when comets experience peak solar heating, we'll get better constraints on composition and mass loss rates. If orbital residuals grow, showing clear, non-gravitational acceleration that helps distinguish between competing models. If spectroscopy reveals the predicted compositional evolution, stronger water emission replacing CO2 dominance that supports the transition hypothesis. If high-resolution imaging shows fragmentation, multiple active regions, or complex morphology that explains anisotropic emission without requiring exotic interpretations. 3 scenarios remain possible. Scenario 1, confirmed natural comet with unusual but explicable behavior. The compositional model is validated, projection effects are quantified, and 3I Atlas joins the catalog as an interesting but ultimately understood object. This remains most likely. Scenario 2, persistent anomaly. Some observations resist natural explanation even after thorough analysis. Not enough to claim artificiality, but enough to keep questions open.
This would be frustrating, but honest, acknowledging we don't fully understand what we're seeing. Scenario 3, genuinely anomalous signatures that force serious consideration of artificial origin. This remains highly improbable, but the data collection and analysis protocols exist to test it rigorously if evidence points that direction. Why does uncertainty persist? Because nature doesn't owe us clear answers on our timescales. Because observation is limited by technology funding and the fundamental challenges of characterizing small, distant, fast-moving objects. Because science is a process, not a destination. Every answered question spawns new ones. Every mystery resolved reveals deeper complexities. That's not failure. That's how understanding grows. What has 3I Atlas taught us, regardless of which scenario ultimately proves correct? First, we're getting better at detecting interstellar visitors.
From Oumuamua's near miss to Borisov's better observed passage to 3I Atlas's relatively early detection, our capabilities are improving. Second, rapid response networks work. The coordination between discovery surveys, spectroscopic facilities, space telescopes, and specialized instruments has matured. We're building infrastructure for studying transient phenomena. Third, the next visitor will find us even better prepared. Rubin Observatory coming online. Foremost spectroscopic capability. JWST's infrared precision, these tools will transform interstellar object science. Fourth, public interest in these discoveries is real and valuable. When people care about what we're studying, funding becomes easier, careers become viable, and the next generation of scientists gets inspired. Fifth mystery is okay. Living with uncertainty, continuing to investigate without premature conclusions, maintaining intellectual humility. These are strengths, not weaknesses. The call to action is simple. Stay curious. Whether you're a professional astronomer, an amateur observer, or someone who just likes looking up at the night sky, 3i Atlas reminds us that the universe still has surprises. Keep watching. Keep asking questions. Keep following the story. Because this story isn't over. Post-perihelion observations are ongoing. Data analysis will continue for months. Papers will be published throughout 2026 and beyond. And the next interstellar visitor could be discovered tomorrow, or next month, or next year. When it arrives, we'll be ready. Better telescopes, better protocols, better understanding of what to look for and how to interpret it. Each visitor teaches us. Each one adds to the growing database of how planetary systems beyond our own construct and eject small bodies. Amateur astronomers played a role too. Dobsonian power, capturing striking solar telescope images of 3i Atlas just hours before solar conjunction. Citizen scientists processing public data. Social media communities discussing observations and theories. This democratization of astronomy, where anyone with telescope and clear skies can contribute, enriches the field. Brings diverse perspectives. Sometimes catches things professionals miss because they're looking elsewhere. The cosmic perspective that studying objects like 3i Atlas provides is valuable beyond pure science. We're temporary inhabitants of a small planet watching messengers from distant places pass through our neighborhood. Those messengers remind us the galaxy is vast. Stars are abundant. Planetary systems form around most of them, and the stuff of planets, ice and rock and organic molecules gets ejected, traveling between stars, sampling the diversity of cosmic environments. We're part of that story. Our solar system formed from material that might have included interstellar grains.
Earth itself incorporated atoms that traveled through space before our sun even existed. 3i Atlas is a cousin in that sense. Not biologically, obviously, but cosmically, made of the same fundamental stuff, shaped by the same physical laws, traveling through the same galaxy. Whether it's entirely natural or something more, it's a reminder that we're not isolated, not cut off from the broader cosmos. Visitors arrive, information flows. The universe is connected in ways we're only beginning to map.
As you drift towards sleep tonight, consider this: somewhere between Mars and Jupiter, though receding rapidly, now an ancient wanderer continues its journey. Whether it's frozen water and rock from a distant stellar nursery, or something that once carried purpose across the light years, it holds secrets we've only begun to uncover. Are we alone? It's the question humanity has asked since we first looked up and wondered if those points of light were places like home, since we first imagined that the universe might be vast enough to hold others like us. 3i Atlas doesn't answer that question, not definitively, not yet, but it reminds us that the question is real, that interstellar space isn't a barrier but a highway, that objects, whether ice or something else, do travel between stars, that our solar system isn't sealed off, isn't isolated, isn't the only collection of matter our sun will ever host. In the coming weeks, as 3i Atlas rounds the sun and begins its long journey back to interstellar darkness, we'll collect more data, run more analyses, build better models, test hypotheses, refine estimates. Perhaps we'll converge on clarity. Perhaps the compositional model will hold up under scrutiny and we'll understand exactly what we witnessed. A comet from a cold outer disk, layered with unusual stratification, expressing those layers through changing activity as solar heating penetrated its interior. That would be satisfying. Clean. Understandable. It would confirm that our physics is robust. Our models are sound. Our understanding of nature extends to visitors from other star systems. Or perhaps anomalies will persist. Small inconsistencies that don't quite fit. Observations that resist explanation even with generous assumptions. Not enough to claim extraordinary origins, but enough to keep questions alive. That would be frustrating. Honest, but frustrating. Science lives in that space more often than popular imagination realizes. Most mysteries don't resolve cleanly. Most questions lead to deeper questions. Or, and this is the option that keeps some of us awake when we should be sleeping, perhaps evidence will accumulate past the point where natural explanations suffice. Perhaps we'll find ourselves forced to consider possibilities we're not ready for. I'm not predicting this. The probability remains vanishingly small, but the universe has surprised us before, often. The history of astronomy is a history of expected patterns, breaking of assumptions, failing of reality, being stranger than our most creative speculations imagined. Here's what I know for certain. The universe has waited billions of years to be understood. It can wait a few more weeks or months or years for us to look more carefully. What keeps me awake isn't the fear of missing something artificial. It's something subtler. It's the recognition that we're at a threshold, a moment when our instruments are finally good enough, our methods refined enough, our understanding deep enough to seriously investigate questions that were pure speculation a decade ago. We can detect interstellar visitors now. Not just guess about their existence, but actually see them, track them, characterize them. That's new. That's extraordinary. And with that capability comes responsibility to look carefully, to think clearly, to distinguish real from artifact, to follow evidence without being led astray by wishful thinking or refusal to consider uncomfortable possibilities. Whether 3i Atlas is ice or something else, it's already succeeded in making us better observers, better thinkers, more aware of our assumptions and limitations. That's valuable. That's worth celebrating. The comet will fade from view eventually. Its brightness will drop below detection thresholds. Telescopes will move on to other targets. The flood of papers will slow to a trickle. But the questions will remain, and the infrastructure we've built. The rapid response networks, the multi-wavelength campaigns, the international coordination will persist. The next visitor will find us ready, and maybe, just maybe, one of these visitors will carry an answer to the question we've been asking since we first looked up, to the mystery that has haunted every human civilization that ever wondered if those lights in the sky were alone or accompanied. Are we alone? I don't know. Nobody knows. Not yet. But objects come from interstellar space. They pass through our neighborhood. They can be studied. And everyone that arrives carries a chance, remote but real, of teaching us something that changes everything. Sleep well. The cosmos will still be here in the morning, and so will the mystery. In the shadow of Mars, something exhales. In the light of our sun, ice transforms. And in the vast darkness between stars, ancient travelers continue their journeys, carrying secrets we're only now learning to read. The universe waits patiently. It always has. It always will, until we're ready to understand what it's been trying to tell us all along.